Okay, good. Yep.
Okay, great. All right. Yeah. So I'd like to thank you for the opportunity to give this talk. It's really been a great seminar, great series, and so I've been really interested to see all kind of the different work in this thing. So I really appreciate the opportunity to give a brief kind of overview of some of our work in developing a layer parallel approach for training deep neural networks. So as I said, my name is Eric Sear. I'm from Sandia National Lab. This is joint work with a large number of people: Stephanie Gunther, who's the Fernbach Fellow at Lawrence Livermore, Lars Rothoto at Emory, Jacob Schroeder at UNM, Nico Gauger at TU Kaiserslautern, Gordon Moon, who's now in South Korea at the Korean Aeronautics University, and Ravi Patel, who's a staff member at Sandia. So I'm going to start off kind of slow. So we'll start off by, in my kind of standard way, defining what a neural net, my view of a neural network. And there's a lot of different perspectives. We've seen graph neural networks, we've seen all kinds of deep nets and all this stuff, but generally the structure kind of sort of follows this kind of form. So a neural network, and from my perspective, is really just a parameterized model where we take an input, and then we have some parameters and then some output, and we'd like to learn the kind of mapping from X to Y as specified by some data. And typically this is composed of multiple layers. So in this case, we talk about these feature vectors used here. We have our input data, and we go through an affine transformation defined by A0 and B0 in this case. And then and that defines kind of our first kind of feature vector. The next feature, then we can iterate this in a kind of a layer-wise fashion, where each layer is defined as this kind of this activation function, which I'm writing kind of very abstractly as F here, this mapping from layer I to layer I plus 1, subject to these parameters AI, BI. Of course, we all know, or we've all kind of experienced this by now, that this is typically an affine transformation of UI subject to some pointwise nonlinear activation function like ReLU. And then I tend to just write it like this. At the final layer, I always have this linear layer at the end. Of course, your mileage may vary here. But again, AL is learnable. And so the parameters then are just kind of the combination, the union of the layers of each layer, the parameters from each layer, AI and BI, and then the final layer. Again, nothing new here, really. So in supervised learning, we have input and output. So we want to learn this mapping from input to output, XI to YI. And so we end up the way we do this is by finding our parameterization, our parameters for our neural network that minimize the loss over this training set. And so I've defined the loss here kind of in a pointwise fashion over the data set, so that what it's trying to do is kind of minimize the difference between the neural network prediction here and the observation here. Okay, so if it can find those parameters that minimize this, we say that we have trained this model, we've learned whatever predictions kind of are implied by the training data. All right, so the loss then is a function then of the loss is just a function that defines the difference between the model and the data. And so we have just a standard regression, kind of L2 loss and cross entropy loss here that would be used in classification. All right. So what does training really mean? Typically, this means some sort of gradient descent. We've seen a few different variations on this, but often they just end up, they all have to kind of, if you're going to do a gradient-based optimizer, you're going to have to take the gradient of this kind of objective function at some point. And the way this works is you do a forward propagation that gets you kind of on the manifold that's represented by the neural network, the neural network evolution, And then you compute what's called the back propagation to compute the gradients. Okay, so this process is kind of best, and I think of it visually. So we do this really slow, this kind of sequential forward propagation where we take the input, we compute each feature through this network. And so we have to do this in a very serialized fashion where we're just passing information from left to right and so forth and so on. So we get to the output, and that puts us on kind of the solution, the kind of constraint surface that's represented by the neural network forward propagation. Then we compute a back propagation. If you're familiar with PD constraint optimization, I would typically say an adjoint. But you do this with back propagation. And so you transfer information from the forward solution to the, you have to save the features from the forward propagation so that you can then linearize about those and compute the gradient. And so there's this coupling between the forward and the backward problem to compute this gradient. And so there's different ways to handle it, but in general, this is kind of a slow process where you go forward for a little bit, and then you go backward and you get a gradient, then you do the whole thing again. And so there's different ways to accelerate this. You know, there's checkpointing, which would allow you to maybe not store some of these states along the way. But in general, this is an expensive process, and people tend to just go ahead and store these things anyway. All right. So another approach that really has kind of revolutionized machine learning and the use of neural networks and deep learning specifically is the notion of parallelism. And so one can kind of see that the rise of machine learning, not coincidentally, came with the rise of GPUs and really kind of high density compute capability. And so parallel computing is really important to training, as the kind of bottom line there. And generally we do it, you know, focus on GPU level parallelism, thread level parallelism on relatively small clusters of GPUs. And so there's kind of different options that you might have in this context, okay? So if you're familiar with the PDE world and the parallelism in that world, you can think about the first one is kind of a parallelism in terms of UQ, where you would want to sample different points in some sort of parameter space, and then you would solve the PDE and push that through in an embarrassingly parallel fashion. Similar, this data parallel scheme for neural networks, where you have replicated the neural network on each processor, and then you can push through different subsets of the data of your training data on each processor, kind of in an embarrassingly parallel fashion. So you do that forward propagation, then you do the backward propagation to compute the gradient. And then because the loss is typically just a linear combination, you just have to do an all reduce to kind of compute a global gradient. And people do different things to kind of accelerate this and maybe eliminate the need for kind of this global communication. But in general, that's the general structure that really exploits a great deal of parallelism you might have in your training algorithm. A different approach that we're kind of been exploring at Sandia and other places is notions of model parallelism. So in this case, your an individual data item might actually be too big to fit on a GPU. We have examples of this where we have, you know, 2000 by 2000 by 2000 CT scans, a voxel image CT scan, where just to do kind of store the data on a single GPU becomes a actual burden, computational burden. But we still want to kind of learn from that data. And so what you end up doing in this case is you can break up the neural network, the evaluation of each neural network layer across processors. Okay, so here you would say, okay, well, this subset of the domain, say subset of the image, is going to be processed by processor 1, another subset is processed by processor 2, so forth and so on. And you have to then do a halo exchange to communicate between them. This works very well in the context of convolutional neural networks, where that exchange is local, and it looks exactly like the kind of parallelism you might see in a spatial decomposition of a partial differential equation. So this is kind of the other approach. Now, both of these approaches are kind of specialized, and they handle two different particular growth mechanisms you might have in a training problem. So if your data set gets larger, you can always do data parallel. If your data items get very large, you might do model parallel in this context. So those have been existed for some time, and they've been approaches that people have used, although the software maturity, I think, is the maturity of the tools is still a little bit limited, although that's growing rapidly in the model parallelism case. So another question, another dimension of the neural network, which neither of these models kind of address, is the growth in depth. So if you have a neural network, and it's 8 layers, but you've decided for whatever reason you'd like to double the number of layers to 4. I'm sorry. You start with a neural network of 4 layers and you'd like to double it to 8. There's really nothing to kind of neither batch, data parallel or model parallelism as defined previously is going to really reduce that runtime. And so if you're really interested and you want to get to 128 layers or 512 or something like that, then maybe this becomes a computational burden that you can't overcome. And note that this isn't really going to be solved by a bigger computer, right? As you go to if you do data parallel or model parallelism, you run into kind of a strong scaling limit where either the stochastic gradient descent algorithm might break down with too much data parallelism, or you run into kind of a traditional strong scaling limit for model parallelism, kind of the spatial parallelism, where adding additional processors don't really do you any good because you have the communication cost relative to the computational work is simply too high. So this is a kind of parallelism we're going to attack. And in general, one can ask the question, well, do you really need a 500-layer ResNet architecture? And I think it's arguable that you probably don't. There's also this development of these neural ODEs where you would discretize in some sort of time dimension as opposed to a layer. That could lead to deeper neural networks. The last one, and the one I'll kind of spend the most detail on today, is in recurrent neural networks. Here, the depth of the kind of evaluation that I'm thinking about is actually defined by the data itself. And so really, if you have, say, a very long movie, a spatial parallelism or a model parallelism might not be as effective for training and accelerating training as you might need. And so how do we address these kind of the growth with the depth in the neural network? So before I kind of talk about the algorithm that we use to do this, I'd like to make a transformation that I think is a very useful one. And the idea here is to take the loss that we have and say, oh, well, this neural network evaluation, we can replace that with the output y here. Okay, so all I've done is I've kind of taken this neural network that I wrote here and wrote it now as a constrained optimization problem. This training problem is this constrained optimization problem where I have kind of unrolled the neural network in the constraint. Okay, what this allows us to do, and this is just kind of an algebraic trick, there's really nothing special about this kind of structure, but what it allows us to do now is to think about these equalities as approximate. Okay, so what we're going to do is we're going to allow ourselves to relax this equality statement here, and then what that inexactness actually makes room for kind of sneaking in parallelism and doing notions of domain decomposition in that structure. but the key then will be to add convergence for this kind of training problem to then recover these equalities, right? So it allows us during the training process to deviate from that, take advantage of it by doing something a little bit faster, and then only at the convergence you actually end up kind of recovering the equality. In fact, we already saw this a little bit earlier today when George Karniadakis talked about his domain decomposition algorithm. He had his little dolphin, and he was using a penalty to tie those things together. He was allowing if I understood the approach correctly, he was allowing the boundary of the dolphin to be inexactly kind of matched at intermediate phases of the neural network training, so that only at convergence does he kind of at some notion of convergence or minimization, does he actually guarantee that those things match. But in doing so, he is able to actually get more parallelism out of his training algorithm. So I've now kind of talked at a high level about what we're going to be going into. The kind of motivation here, of course, is that training neural networks can be costly, kind of weeks of time to really do these things. There's lots of data to look at, lots of weights and features to optimize. These are all expensive operations. And so the question is really, can parallel computing in general and high performance computing kind of as a familiar to the kind of PD simulation world, really, or scientific computing world, be of help here. And already, these GPU codes are really helping. And I'm, really enthusiastic about kind of the degree of optimization algorithms that we're seeing being developed both here and elsewhere, and as an opportunity for both kind of faster training, but also the opportunity to introduce different levels of parallelism, different approaches to parallelism. So the rest of the talk will really concern kind of this layer parallel idea specifically. So, I drew those pictures of data parallel and model parallel before. This is kind of the obvious extension to layer parallel, where you put each layer on a subset of layers on each processor, and then you want to be able to do kind of local work on each processor, and then communicate the kind of connection between them, kind of at some convergence. So we're going to try to. So the way we're going to do that then is we're going to assume an inexact evolution. As I said, that's kind of a repeated theme. You'll see it at least once more. And then we try to stitch them together in some way at the end so that we actually converge to a correct neural network solution. So, I had a postdoc and he started at Sandia, and the first thing he did is, of course, went and presented his thesis work at supercomputing. And he was talking to his friends and he said, well, okay, this layer parallel idea really makes no sense. They're kind of right. So you have a gradient descent algorithm where you're doing a forward propagation. This is a serial thing. If you remember that really slow, boring movie from before, we saw forward propagation is necessary. And then we have back propagation, where we kind of move backward through the neural network, again, slow and boring. And then we update the weights and biases with the gradients, with the computed gradients. So because these things are serial, it really doesn't make a whole lot of sense to then do this layer parallel approach, right? But of course, I've already motivated what we're going to be doing. We're going to relax the exactness kind of assumed in traditional forward and back propagation by introducing an error. That error is going to be controlled by whatever algorithm that we're going to use to actually introduce that error. But ultimately, it will give us an approximation to the forward propagation that we can exploit to get kind of better performance. And so just by doing this simple trick, which is a very common trick in numerical methods. So like we know how to exactly invert matrices, but we tend to use Krylov methods because they're much faster. Those are really just inexact kind of inverse operations. So this trick is very common in numerical methods. And so we're going to try to exploit this in the machine learning context, in this neural network context. And so I'm going to actually do this through a multigrid algorithm, which I'll explain here momentarily. There's one last transformation I'd like to make just to make my storytelling a little simpler. We're focusing on ResNets. The reason for this really is that the ResNet architecture is more stable at large number of layers than, say, the traditional kind of feed-forward neural network, which suffers, say, from vanishing gradient problems. And so one transformation that's been recently developed is to transform this kind of ResNet architecture into an ODE. So the way you do that is by pretending at each layer you've got some little delta t parameter here, and you'd recognize this as explicit Euler time discretization, and you transform that by taking delta t to 0. And so now your layers are represented by basically the time value, and you end up solving this ODE for the neural network instead of this kind of algebraic kind of equation. So there's a number of different papers about this, both this paper in NeurIPS several years ago, and the stable architectures that Lars and Eldad Haber put together. So with this formulation, this time-dependent formulation, we can start to leverage some of the existing methods in the say PDE community or ODE community that use parallel in time. So there's a nice review article by Martin Gander on this, but the kind of highlights for me are this parareal algorithm, which was, very classical and kind of started the resurgence in parallel and time algorithms. The FAST algorithm by Michael Minion and collaborators, that's kind of an extension of that approach. And then a very kind of similar algorithm is this multigrid in time kind of approach developed at Lawrence Livermore. And this is the kind of approach that we'll be taking in this talk. All of these algorithms kind of do the same type of thing, where they do a decomposition of the problem into kind of coarse kind of evolution and then kind of fine corrections, okay? So in the multigrid context, what we're going to do is we're going to take our fine grid neural network, say, that has 8 layers, and we're going to take a subset of it that, say, only has 4 layers, okay? On the fine level, we're going to be able to do local work where we just assume that the kind of initial guess, say for layer 3, came from whatever kind of previous information we had about the output of layer 2. Okay, and then we're going to do a relaxation here. So we're going to basically do several sweeps of forward propagation in this case. And that produces a local approximation of the state of the neural network. Then we're going to transfer that approximate state to the coarse grid and say, okay, that we know that's inaccurate because we've not resolved these kind of discontinuities here. And so we'd like the coarse version to resolve this discontinuity by propagating serially. Okay, so now we do a cheap but serial operation on the coarse grid and produce a correction to bring back to the fine grid. Okay, so the fine neural network now has a correction that has global information, kind of end-to-end communication throughout the whole neural network, even if it's at this kind of coarser representation. Now it takes that correction and then uses that to update its, to locally update in an embarrassingly parallel fashion each of the states for the neural network. Now you can repeat this process kind of multiple times, where you go through the exchange between fine level and coarse level back to fine level until you actually achieve convergence for the forward propagation. So basically, you don't really have the you always have this discontinuity until you actually reach some sort of convergence within this kind of iteration. And for the forward propagation, for instance, you can do this kind of in a multi-level context by just recursing again, and so that you have you assume that this coarse problem isn't coarse enough, you coarse in again, and you have, say, a 3-level method or a 5-level method in this multi-grid idea until you get whatever performance that you kind of require. And so we do this for both the forward propagation, and if you reverse all the arrows, we do it for the back propagation too. Okay. So then how does this algorithm work? So we've tested this on these ResNets using kind of 3 different kind of problems. We have the peaks problem that Eldad and Lars put together, where the idea is to classify the location of point clouds in a level set, which level set they belong to. You also have the Indian pines, and this is a hyperspectral imaging thing. You're trying to determine if this field is corn or soy or like chinchillas or something. And then you have MNIST, which is the classic handwritten digit representation. So the first set of results that I'm going to show are based on the XBraid code. Well, they're all based on XBraid, but we actually wrote a hand-rolled C++ neural network code just to kind of work through the details of how one might go about doing this. And so the neural networks for these problems are not optimized. You certainly don't need a very deep neural network to do MNIST, for instance. And then the performance isn't really tuned. So I'd like you to kind of bear that in mind as we're looking at the results. And then know that we're spending more time on this now to make sure that the performance is kind of where it needs to be in the serial evaluation. All right, so for these 3 problems, what we have here is the training loss and the validation accuracy. So the training loss here is the solid lines. The validation accuracy is these dotted lines as a function of iteration or epoch in this case. And here we're using the layer parallel is in purple and layer serial is in cyan here. And what this is showing is that both for the peaks and the Indian pines problem, despite the fact that we're doing this kind of inexact forward and backward propagation, both the loss and the validation accuracy is matching well the serial version of the code. So we're not really being penalized from an accuracy standpoint for these problems for actually doing this inexact forward and backward propagation. So then the question is, how does the speed up actually work? Well, if we do a weak scaling study, this is where the neural network gets deeper as we add more processors. And so we're able to kind of run a larger neural network. We see that the runtime is basically flat. It doesn't grow with deeper neural networks, but we're adding more processors to balance that out. So this is kind of ideal weak scaling, showing 10x and 16x kind of speed ups for both Indian pines and MNIST out to 2048 layers. Pretty deep layers and 512 cores, okay? In the strong scaling case, we have a fixed number of layers, and we're just kind of trying to accelerate the training algorithm by adding more processors and doing the layer parallel decomposition. We see that we get good strong scaling, especially for the deeper neural networks. This is a feature of multigrid in time, where it actually does work better as things get deeper or you have more time steps. So this is kind of the expected behavior, where if you have relatively few time steps, in this case 256, you see that we're only breaking even at around 16 processors. We've now been able to shift these things down a bit, so that even at like 128 steps, we're able to get speed ups at 4 processors. So we're moving in the right direction, but that's really a very big challenge with any parallel time method. All right, so the prior algorithm that we were using was actually more of a kind of second order optimization method. Here I'm looking at how neural networks actually work in how we can actually use layer parallel in the context of stochastic gradient descent, and if this actually works just as well. So to start with, I looked at these fashion MNIST. Okay, so it's nice because it's a very small problem, but it's known to be harder in some sense than the standard kind of digit MNIST data set. Okay, it's harder to achieve good accuracies, basically. And so what we can see here is that regardless of the number of processors we use, if we use serial or parallel, the algorithm, the training actually gets to kind of the same level of accuracy as the serial algorithm. So this is kind of what we want to see, is that despite doing this inexact thing, like I talked about before, we're actually doing very well in terms of test accuracy for the training. All right, so I want to shift gears a little bit from the kind of ResNet image classification type problems I was just talking about to more sequence classification problems. So in sequence classification, you have a sequence of input kind of data. So you would have like a time series, or maybe it's a video. In our case, it'll be videos in time series, where you want to take that operation, the sequence, and map it to a particular class in this case. And so we'd like to really learn phi here, which is that mapping function. And so the solution that's been come up with over several years, at least one of the solutions, is recurrent neural networks. So what a recurrent neural network does is it takes as input the sequence, okay, and produces a hidden state. That hidden state is then passed to the very same neural network, neural network, and that one takes a new entry in the sequence and then passes it along. Okay, so basically, this queue is going to then be basically sliding over the sequence, and you're going to kind of iteratively maintain a hidden state, kind of based on the observed sequence between entrances, values in the sequence. In the final layer, you have the output of the hidden state, and you can do classification or regression. There's also cases where you might just do a straight up transformation of this sequence to some other sequence. We haven't looked at that. I don't view that as kind of a substantively different problem, but it is an interesting next step for our work. If you're interested in recurrent networks, you should look at this Cola's blog. It's basically the best discussion I've found. I'm not in love with the LSTM paper that I originally read about this, but Cola's blog is a pretty good description. So over the years, they've kind of come to realize some of the challenges of recurrent neural networks, and have kind of overcome that with two different distinct architectures. There's the long-term, short-term memory LSTMs and generalized recurrent unit neural networks. And I'm going to focus on the generalized recurrent neural network here. In this case, what happens is you've got this, the hidden state is written in this kind of update equation. So you have some sort of ZT that's computed from these weights and biases on the sequence data. And you can update this hidden state using this kind of expression here. So these equations really just encode the weights and biases and produce an evaluation that is then kind of used for this evolution expression. Okay, so this is the expression I actually kind of want to pay the most attention to in this discussion. So I looked at this a little bit, and before I mentioned that we did this transformation to an ODE form, and I think that's a really useful transformation from the multigrid perspective, because typically in multigrid I require a coarsening operator, a representation of somehow a bigger step. And so a natural way to do this is with a bigger time step. And so I actually introduced this, and using delta t equals 1, I add and subtract the ht minus 1, and then I get this kind of updated GRU formulation where I have a delta t here that represents our fictitious time step. But of course, I can take that fictitious time step to 0 now, and I can learn a little bit about how GRU might actually work. So when I look at this ODE that we get from this, you see that this is a stiff mode, okay? So this is basically a mode that's collapsing onto some sort of multi-rate at some multi-rate kind of asymptotic. This is basically a dissipation term. So it's taking all the kind of old information and kind of deciding on a fixed hidden state that represents it. And then we've got this kind of other term where we're introducing new sequence information. We're injecting more information, basically energy into this system to push us off the kind of the collapsing asymptotic and hopefully incorporate information. And so this is, in a sense, this kind of memory notion. It's just being kind of propagated through some sort of ODE term that has a asymptotic long-term behavior. So when I think about it this way, it kind of suggests that there's a problem. If I want to take delta t equal to 1, and then I double my time step size, it may be that stiffness reveals itself as instability on the coarse grid in the multigrid context. So that's going to be a problem. And so what we end up doing then is say, oh, okay, well, I know where that stiff term comes from. This term here is the stiff part. So I'm going to put it on the left-hand side and make this thing implicit in this stiff term. So I'm changing the GRU algorithm now a little bit. And when I do that, it allows me to actually take bigger time steps and step over this stiff mode, this kind of this stiff decay here. But still kind of incorporate kind of the instantaneous information from the sequence data. So we're going to leverage this in the multigrid and time solver. So there are different options that we can use for this, but the basic idea here is that I want to do this implicit GRU on the fine level using delta t equal 1. So I'm going to be very close to what a standard GRU is, but I'm going to just set delta t equal to 1 on the finest level, and then use on the coarse level bigger delta t. So I have a couple of examples here. We have got human activity recognition using smartphones. This is a really small data set. You have 6 labels. Each sequence has 128 steps with 9 features. We're going to run this through the GRU approach. And in general, for GRU and LSTM with 5 to 10 epochs on atom, you can get to 90% test accuracy. So this is a really easy problem. And so, we're not going to get great speed ups here. You can see here for the parallel GRU here, we're able to get about 2x speed up over the serial version. We use a lot of processors to get that speed up, but we're able to actually get speed ups. And then the other question, and there's 2 aspects to this other question, is the classic GRU, say the explicit GRU, as good as the implicit GRU as good as that? That comparison you can see with the dashed lines, the black lines, they are basically pretty much the same. So implicit GRU and serial GRU are kind of in the ballpark doing the same thing. Then we can ask, well, okay, how does our parallel GRU work if I'm using a parallel inference? So that's this red line here. So this is as trained, basically. the parallel GRU actually does kind of comparable roughly to the serial versions. The last one is this serial inference. So what this is I take the parallel trained algorithm, take the learned weights and biases, shove it into the serial one, and then do a serial inference. Okay, and because the parallel version has all this error in its propagation, the parallel GRU, the serial GRU, in the serial version does not in the inference. One can ask the question, are those kind of giving you the same answer? Is the parallel inference kind of good enough to be applied in serial? Have we resolved those discontinuities well enough? And the answer is from a test accuracy perspective, we have. In spite of the fact that we're kind of doing this inexactly, the serial inference still works just as well. So going to kind of a more challenging database, we're looking at this HMDB51, which is a large human motion database where we have a large number of classes of different kind of human motion activities. I'm just going to take a subset of those. So we have these videos that show people chewing, eating, jumping, running, sitting, and walking. And we're going to kind of train on this neural network and see if we can train on this subset data and see how well we do in the classification and the testing. A comment I'll make about this, because it's relevant from a performance perspective. If you do this, our architecture uses a pre-trained ResNet 18 to take each frame from of an image to some sort of classified or some set of features that were pre-trained. And so this is somehow simplifying or reducing the complexity of our recurrent neural network by kind of filtering through some sort of or a pre-trained ResNet to limit the kind of complexity of the classification task. And so what you end up with here is a new set of sequences that are just based on using this kind of ResNet architecture. A few details, we have a batch size of 100, we're using Atom, and then I'm very careful to not apply ResNet 18 on the coarse grids of my multigrid scheme. And this is because I really don't need to. I've already evaluated on the fine grid, so I might as well just reuse them on the coarse grid. And so that's what we do. So each image for both the serial case and the parallel case, the feature is only computed once. This is saving some computational effort. So in terms of loss for the different versions, so we've got the implicit in parallel and the classic in serial. We see that the loss is kind of decaying kind of equivalently. These are very similar results in terms of the training. And then the accuracy is kind of in the same ballpark for all of them. And so that's kind of what we want to see. And I will say that the implicit one, if I then shove that those weights and biases into the serial inference implicit GRU algorithm, those actually work just as well as the kind of parallel accuracy. So as before we saw with the previous data set, we haven't really lost anything by doing this inexactly. For this case, we have 128 processors, 128 time steps. We're able to get to 7x parallel speed up with 32 processors. So this isn't ideal parallel efficiency, but it is showing that we can get real speed ups that can actually really help our problem. And if the data set gets deeper, so for instance, in the kinetics 400 data set, it's 256 frames basically. We can expect kind of better speed ups as we go to longer problems. So that's a kind of a scaling curve that we want to be on. To kind of break this down a little bit, I'm interested in seeing where I'm getting performance benefit. So I've broken this down. This is a linear scaling, time scaling plot. So here we can see that these things scale really well, just like we saw in the previous for the total computation. It's probably a little bit easier though to look at the log plot, but it's just not as pretty from a performance standpoint. So we see that basically the forward time is dominating here. Even for the serial algorithm, and the backward isn't nearly as expensive. This is something I haven't dug into, but I'm pretty interested in kind of figure out why that we have that strong disparity. There is some disk read where I'm reading these movies from disk kind of constantly through the algorithm. The parallelization gives you better performance here because you're able to kind of spread that out over more processors. So that's an added benefit, but I think it's one that's kind of a little bit false because we can always cover the disk work with the forward work. So that's some further improvements we need to do to our algorithm. So that's kind of the end of the algorithmic discussion. I will say we have a code, we call it torch braid, that combines kind of PyTorch and an X-braid, and those previous results for recurrent neural networks are based on that. It has a computer architecture, which I'm happy to talk through if you're interested. And then let's see, and so it gets good speed ups. Okay, that's what we've seen in the end. Even for the ResNet case, I'm able to get to 30x speed ups for fairly deep neural networks on relatively few processors. And we do this with kind of no accuracy loss, really, in terms of test accuracy. So I want to close here, and I will say we are hiring. So if you're interested, feel free to reach out. I'd be really excited to hear about anything you're interested in, if you'd like to work with me or the team at Sandia. The thing I want to kind of point out, maybe the highlight here, is that parallelism is really exposed by permitting inexact propagation. We've done it in these kind of time sequences, these very deep neural networks, but one can imagine other regimes where by doing this constrained optimization approach, you can open up other kind of inexactness that leads the way to parallelism. And so that's really kind of maybe the take-home message I'd like to kind of deliver. If you're interested, here are papers. This Simod's paper is probably the core one that's focused on layer parallel. That's the one I'd point you to initially. I'd like to thank the DOE Office of Science Early Career Program for this support. And I think with that, I'll close and take any questions. Thank you very much.
Eric, thanks for the nice talk. So any questions to ask? So